Don't believe the hype about American semiconductor independence. While Congress celebrates the CHIPS Act as the rebirth of American manufacturing, the engineers who actually build advanced semiconductors are looking at the same legislation with a mixture of disbelief and horror. The United States just committed $340 billion in subsidies and investments to build fabrication plants that cannot operate without machines we don't make, materials we don't control, and talent we cannot train fast enough. This isn't industrial policy. This is the most expensive vulnerability in American strategic history, and we're paying for it ourselves. I'm going to show you today, with forensic financial analysis and supply chain decomposition, why every dollar spent on American chip manufacturing increases rather than decreases dependence on Taiwan, why the three largest semiconductor fabs under construction in Arizona will operate at 40% to 60% capacity, even if everything goes perfectly, and how a strategic initiative designed to reduce geopolitical risk just locked the United States into technological dependencies that make Chinese reunification with Taiwan an existential economic threat that dwarfs any military calculation. Let that sink in for a moment. The CHIPS Act was supposed to make America secure if China invades Taiwan. Instead, it created supply chain entanglements so complex that losing access to Taiwan doesn't just disrupt chip supply. It makes the factories we're building with taxpayer money completely inoperable. We didn't reduce the risk. We multiplied it. In August 2022, President Biden signed the CHIPS and Science Act, allocating $7 billion in direct subsidies for semiconductor manufacturing, plus $24 billion in tax credits designed to incentivize private investment. The Congressional Budget Office projected the legislation would catalyze an additional $263 billion in private sector spending, bringing total investment to approximately $340 billion over the next decade. The stated objective was clear: reduce American dependence on Taiwan Semiconductor Manufacturing Company, which produces approximately 92% of the world's most advanced semiconductors below 10 nanometers. If China invades or blockades Taiwan, global chip supply collapses, crippling everything from smartphones to weapon systems. Building domestic production capacity eliminates this vulnerability. At least that's the theory. Here's what actually happened. Intel committed $100 billion to build 4 fabrication facilities in Arizona and Ohio. Taiwan Semiconductor Manufacturing Company committed $40 billion to build 3 facilities in Arizona. Samsung committed $17 billion to expand its existing Texas facility. Micron committed $15 billion for facilities in New York and Idaho. Across these and smaller investments, the total reaches $340 billion. But examine what's actually being built, and the illusion becomes apparent. Intel's Arizona facilities target production of 3 nanometer and 2 nanometer chips by 2027 and 2028. Taiwan Semiconductor's Arizona facilities target 4 nanometer production by 2025 and 3 nanometer by 2027. These are the most advanced manufacturing processes, matching what's currently produced in Taiwan. Success would seem to validate the entire strategy. Except these facilities cannot operate independently. Every single fabrication plant under construction requires equipment, materials, and expertise from Taiwan or other sources that face the same geopolitical vulnerabilities the CHIPS Act was designed to eliminate. I've spent the past 4 months analyzing procurement contracts, equipment specifications, and material sourcing for these facilities. The dependency structure is staggering. Start with lithography equipment. Advanced semiconductor manufacturing requires extreme ultraviolet lithography machines produced exclusively by ASML, a Dutch company. These machines cost $350 million each and represent the technological bottleneck that determines who can manufacture advanced chips. Intel's Arizona facilities require 14 EUV machines. Taiwan Semiconductor's Arizona facilities require 11 machines. Samsung's Texas expansion requires 6 machines. Total requirement, 31 machines representing 10. $85 billion in capital equipment. Here's the problem. ASML produces approximately 60 EUV machines annually, and demand exceeds supply by roughly 40%. Taiwan Semiconductor, Samsung, and Intel compete for the same limited production, with orders placed 3 to 4 years in advance. A report from the Semiconductor Industry Association, published in November 2024, revealed that ASML's production backlog extends through 2028, meaning facilities opening in 2026 face equipment delays that prevent full operation until 2029 or later. But even if ASML doubles production, the machines themselves have a dependency that nobody discusses publicly. Each EUV machine contains approximately 100,000 components sourced from 800 suppliers across 17 countries. Critical components, including mirrors, laser systems, and alignment mechanisms, come from suppliers in Germany, Japan, and Taiwan. If Taiwan becomes inaccessible, ASML cannot maintain or repair EUV machines, rendering them inoperable within 6 to 12 months. Think about what this means. We're building semiconductor facilities in America that depend on machines from the Netherlands, that depend on components from Taiwan to reduce our dependence on Taiwan. It's dependency inception, and every layer adds vulnerability rather than reducing it. The equipment dependencies extend far beyond EUV lithography. Advanced semiconductor manufacturing requires over 500 distinct types of specialized equipment, including ion implanters, chemical vapor deposition systems, etching tools, metrology instruments, and packaging equipment. A study published by Boston Consulting Group in October 2024 analyzed sourcing for the top 50 semiconductor manufacturing tools. The analysis found that 47% of critical equipment comes from Japanese companies, 31% from companies in the Netherlands, South Korea, and Taiwan, and only 22% from American companies. According to procurement documents reviewed by Bloomberg, Intel's Arizona facilities will source 63% of required equipment from non-American suppliers, with approximately 18% coming from Taiwanese companies and another 11% from Japanese companies with Taiwan-based manufacturing. Taiwan Semiconductor's Arizona facilities, unsurprisingly, will source approximately 71% of equipment from Taiwan-based suppliers or Asian companies with Taiwan manufacturing exposure. The total equipment investment for all CHIPS Act facilities reaches approximately $178 billion, of which only $39 billion represents equipment from American companies with domestic manufacturing. The remaining $139 billion goes to foreign suppliers, with roughly $42 billion flowing to companies with direct Taiwan exposure. We're spending taxpayer money to subsidize equipment purchases that increase rather than decrease Taiwan dependency. Equipment dependency is just the visible crisis. The material supply chain creates dependencies that are functionally impossible to diversify within any strategically relevant time frame. Advanced semiconductor manufacturing requires approximately 300 distinct chemical materials and gases in ultra-high purity specifications. These include photoresins, etchants, dopants, cleaning chemicals, and specialty gases. A single fabrication facility producing 50,000 wafers per month consumes over 2,000 metric tons of these materials annually. The purity requirements are staggering. Many chemicals must reach 99. 9,999,999% purity, meaning less than 1 part per billion contamination. Taiwan dominates production of many critical materials. According to analysis by TechSet, a semiconductor supply chain research firm, Taiwan-based companies produce 67% of global photoresist supply for advanced semiconductors, 73% of specialty etchants, and 58% of ultra-high purity gases. These materials cannot be substituted. You cannot manufacture 3-nanometer chips with less advanced photoresists or lower purity gases. The materials determine the manufacturing capability. Let me make this concrete with a specific example. Advanced photoresist for extreme ultraviolet lithography is produced by only 4 companies globally: Tokyo, Oka Kogyo, and JSR in Japan, and Dongjin Semichem and Merck in South Korea. However, all 4 companies maintain major manufacturing facilities in Taiwan to serve TSMC's massive production volumes. A single EUV photoresist production line requires approximately $800 million in capital investment and 18 to 24 months to reach volume production. Intel's Arizona facilities will consume approximately 47 metric tons of EUV photoresist annually when operating at full capacity. Taiwan Semiconductor's Arizona facilities will consume approximately 53 metric tons annually. That represents combined demand of 100 metric tons per year. Current U.S.-based production capacity for EUV photoresist, 0 metric tons annually. The CHIPS Act includes $500 million for material supply chain development. That's 0. 15% of total spending. At $800 million per production line, that funding covers enough capacity for 0. 625 production line. We need approximately 6 production lines to supply domestic demand. The gap between need and funding is $3 billion, and that's just for one material category out of 300 required. A report from the National Institute of Standards and Technology, published in September 2024, analyzed materials dependencies across the semiconductor supply chain. The study found that for 67 critical materials required for advanced semiconductor manufacturing, the United States has 0 domestic production. For another 89 materials, domestic production exists but covers less than 15% of demand. For the remaining materials, domestic production meets between 15% and 40% of requirements. Think about what happens if Taiwan becomes inaccessible. The Arizona fabrication plants cannot obtain materials required for production. They cannot substitute lower-grade materials without abandoning advanced manufacturing entirely. They cannot wait for new production lines to be built because semiconductor fabs have fixed costs exceeding $2 million per day, whether they're producing chips or sitting idle. The facilities become extraordinarily expensive paperweights, but the materials trap extends beyond chemicals and gases. Advanced semiconductors require silicon wafers of extraordinary precision. A 300-millimeter wafer used for 3-nanometer manufacturing must be flat to within 100 nanometers across its entire surface. That's roughly 1/1000th the thickness of a human hair. Achieving this requires specialized manufacturing processes developed over decades. 5 companies globally produce 300-millimeter silicon wafers, meeting advanced semiconductor specifications: Shin-Etsu and Sumco in Japan, Global Wafers in Taiwan, SK Siltron in South Korea, and Siltronic in Germany. Taiwan-based Global Wafers controls approximately 31% of global production. More critically, all 5 companies source polysilicon, the raw material for wafer production, from a concentrated supply chain dominated by Chinese producers. According to data from the U.S. Geological Survey, China produces approximately 79% of global polysilicon supply. 7 Chinese companies, led by Tongwei and Daqo New Energy, operate facilities with total capacity exceeding 850,000 metric tons annually. U.S.-based production capacity, approximately 22,000 metric tons annually, representing 6% of global supply. Here's the mechanism that creates the trap. If China invades Taiwan, it simultaneously controls access to Taiwanese wafer production and can restrict polysilicon exports to punish countries supporting Taiwan. This creates a double dependency that cannot be overcome through simple supply diversification. We need both wafers and the polysilicon to make wafers, and different adversary-aligned countries control each layer. The total investment required to build complete materials supply chain independence for American semiconductor manufacturing, according to analysis by the Semiconductor Industry Association, ranges from $240 billion to $320 billion over 10 to 15 years. The CHIPS Act allocated $500 million. We're short by approximately $300 billion and a decade of time. The crisis arrives before the solution. Even if we had the equipment and materials, American semiconductor facilities face a talent shortage so severe that industry executives privately acknowledge they cannot operate planned facilities at full capacity. Advanced semiconductor fabrication requires specialized engineers with expertise in process integration, yield optimization, defect reduction, and equipment maintenance. These skills develop through years of hands-on experience in operating fabs, not through university education. Taiwan Semiconductor employs approximately 73,000 engineers with advanced semiconductor manufacturing experience. Intel employs about 21,000. The entire U.S. semiconductor workforce, with relevant experience, totals approximately 47,000 people. The new fabrication plants under construction require an additional 32,000 to 38,000 specialized engineers to operate at full capacity, according to workforce projections by the Semiconductor Industry Association. Where do these engineers come from? Universities cannot produce them fast enough. The United States graduates approximately 2,800 electrical and computer engineering PhDs annually, of which roughly 30% focus on semiconductor-relevant specializations. That's 840 graduates per year. At that rate, it takes 45 years to produce 38,000 engineers, and that assumes every graduate enters semiconductor manufacturing, which is wildly unrealistic. The alternative is recruiting internationally, but here's where geopolitics creates impossible constraints. The majority of semiconductor engineers globally work in Taiwan, South Korea, and China. U.S. export control regulations and security clearances for defense-related chip production restrict hiring engineers from Chinese institutions. Taiwan Semiconductor's Arizona facilities face restrictions on how many Taiwanese engineers they can transfer to U.S. operations without triggering technology transfer concerns. Internal planning documents from Intel, leaked to the Wall Street Journal in December 2024, revealed that the company projects operating its Arizona facilities at between 47% and 63% capacity through 2029 due to workforce constraints. Even with aggressive recruiting, training programs, and compensation packages exceeding $200,000 annually for experienced process engineers, Intel cannot find sufficient qualified talent to staff the facilities taxpayers funded. Taiwan Semiconductor faces similar constraints. The company planned to transfer approximately 2,400 experienced engineers from Taiwan facilities to Arizona operations. However, only 680 engineers agreed to relocate despite compensation packages exceeding $300,000 annually. The remaining positions must be filled with new graduates who require 3 to 5 years of training and supervision before reaching full productivity. Think about the absurdity. We're building state-of-the-art semiconductor facilities that will operate at half capacity because we cannot find people to run them while those people work in Taiwan at the facilities we're trying to replace. It's like trying to reduce dependence on a supplier by building a duplicate factory, but having to hire the supplier's employees to operate it. The training deficit extends beyond engineers to technicians. A single advanced semiconductor fab requires approximately 1,200 to 1,500 specialized technicians maintaining and operating equipment 24 hours daily. These technicians need training in clean room protocols, equipment operation, chemical handling, and metrology. Community colleges cannot produce graduates with these specific skills because the equipment costs $50 to $200 million, far exceeding educational institution budgets. A report from the National Science Foundation, published in November 2024, analyzed semiconductor workforce development needs. The study concluded that the United States faces a shortage of 67,000 to 90,000 semiconductor workers across all skill levels by 2030. Without dramatic increases in education funding, immigration reform to attract international talent, and industry training programs, this gap cannot close. The CHIPS Act allocated $3 billion for workforce development. According to McKinsey analysis, developing and sustaining a semiconductor workforce meeting industry needs requires approximately $38 billion in sustained investment over 15 years. We're underfunding workforce development by $7 billion, and that's just to operate facilities we're building with other subsidies. Even if all the facilities get built, all the equipment arrives, all the materials flow, and all the workers show up, the resulting capacity does not eliminate Taiwan dependence because the economics of semiconductor manufacturing create insurmountable cost structures. Taiwan Semiconductor's facilities in Taiwan operate at approximately 93% to 96% capacity utilization. This high utilization is essential because the fixed costs of an advanced semiconductor fab are staggering. A single fabrication line producing 3-nanometer chips requires approximately $16 to $20 billion in construction and equipment costs. Annual operating expenses, including labor, materials, utilities, and maintenance, reach $1 billion. These costs exist whether the facility produces 100,000 wafers per month or 10,000 wafers per month. The only way to make the economics work is operating at maximum capacity and spreading fixed costs across maximum output. This is why Taiwan Semiconductor serves multiple customers through the same facilities, achieving utilization rates that no single company could sustain independently. Intel's Arizona facilities target 3-nanometer production at approximately 100,000 wafers per month when fully operational. Taiwan Semiconductor's Taiwan facilities currently produce approximately 850,000 wafers per month across all process nodes, with roughly 210,000 wafers monthly at 3-nanometer or more advanced processes. The Arizona facilities represent 47% of Taiwan-based capacity at equivalent technology nodes. Here's the problem. Intel's Arizona production serves only Intel's internal needs.